All right, so this is the third video for day one of STAT 540. I'm going to be talking about exploratory data analysis. So let me start sharing my screen here. And we should have the screen being shared. Okay, so where we're picking up is, I think this was the last slide we looked at the end of the last video. And we were talking about things you do prior to the data analysis. And primarily, we talked about study design. There's a few slides previous to this slide 12 on study design. And then there was data collection and cleaning, organization. And maybe the main takeaway from the previous video was that these are things which are not going to be covered in depth in this class. But they are a huge part of an actual statistical study. And they're going to take a lot of your time as a practicing statistician, sitting down, talking with the other people, the domain area scientists, about what the questions they're trying to answer, what data they intend to collect, talking with you as a statistician about how to collect that data, talking about things like randomization and sample size and things like that. But also, as the statistician, you're spending a lot of time learning their language. And then there's the data collection and the organization, and real data is messy. And so organizing it often takes a lot of time, and often that falls on us, the statisticians, to do that. So we're going to talk about another piece with exploratory data analysis. And so this is after the data have been collected and organized, but you can kind of view it as still prior to the analysis, but maybe it goes hand in hand with the analysis. Some of the exploratory data analysis should definitely be done before you fit your models and you make parameter estimates and things like that. Let's just go through these slides. EDA, exploratory data analysis, it says, are one of the most important parts of any data analysis, and that's absolutely true. And it won't feel that way because this is not something that's talked about in the KNNL book. It's not something we're going to spend a lot of time on this in this class on, but it is very important, very essential to your role as a practicing statistician. So the goals of an exploratory data analysis are to understand the data. Oftentimes that's going to be done by drawing some pictures, making some graphs. But you want to get a feel for the data before you start estimating parameters, because if you explore the data, you want to see if, hey, the model that we're thinking about seems suitable for this. You can also find unusual aspects or errors in the data, making some simple plots. You can see, oh, well, obviously this observation was coded wrong. I work a lot in environmental data sets, and so if I get a negative precipitation amount, I know something's wrong with that data point, right? But that negative precipitation amount would mess up any statistical analysis that we want to run. This one's important. Anticipate the results of a complicated analysis. We're eventually going to fit a model to this data. We're going to try to explain what's going on, and it would be good to know if we think we anticipate that, hey, the slope parameter with one of our explanatory variables is, we expect it to be positive. That makes sense from what we understand from the problem before we even collect the data, but then we make a plot and we see if that seems to fit. plan how to explain data and results to the consumer of your analysis. This is a big one, and I'll come back to it. But ultimately, what we as statisticians are doing is we're trying to tell the story that we think is in the data. And so our data analysis is part of that, and we're going to spend our time learning how to fit models, but really our goal is to tell a story. And so a lot of that story is going to be done with our EDA, where we make some plots and so forth. Okay, so the next few slides are going to talk about 1D exploration, 2D exploration, and so forth. 1D exploration. So what we're going to see here very shortly is, let me jump ahead to this slide. We'll go back. We're going to look at the classic regression example, and that's this goes back well to 1886. This was the first regression analysis, or often referred to as the first regression analysis, and it's where we get the term regression from. So Galton collected data on parents and children's height. So this column here will be children's height. This column here will be father's height and mother's height. We'll take the mean of those two to get mean parent height. And eventually we're going to build a model between these two. But the first thing we're going to do is we're going to look at each variable individually. We're going to look at child height just in terms of child height. We're going to look at parent height, make some summary statistics for those, understand a little bit about each variable, and then we'll do our 2D analysis, where here we've got our explanatory variable of mean parent height. Here we've got this is child height, and we can see kind of what we expect and what we thought. What Galton was thinking was that taller parents tend to have taller children, and we can see a weak positive relationship in this data. So this here is an example of 2D exploratory data analysis. All we're making is a scatter plot. We're looking at two variables, and so that's why it's two-dimension. These previous ones, making a histogram and making a box and whisker plot, that's 1D data analysis. We can, I can't cover it up with my hand here on Zoom, but we could ignore this one completely for a second and just describe what's going on with child height. We see central tendency. We see that the bulk of the data kind of falls between, say, 64 and 70, and then we have some outliers going all the way up to 80 and down to 55. So that would be a 1D data analysis. All right, so working our way back to the slides, I've kind of given the story away a bit, but in a 1D exploration, we describe each variable separately. We would maybe make a table where we talk about mean or median, standard deviation, things like that. And then, as we saw on that slide, make a graphical summary. We might make a histogram, we might make a box plot, we might make a non-parametric density estimate, draw some pictures to understand a little bit about what's going on with the data set and with each variable, I should say. And so for us, that's child height. The other variable that was shown was mean parent height, but we could do it individually for father and for mother, meaning father and mother's height. Okay, and then 2D exploration. The goal here is to study the relationship between pairs of variables, and so that's what we saw in that two-dimensional scatter plot. We had mean parent height on the horizontal axis, we had child height on the vertical axis, and we saw that there seemed to be a positive relationship, that taller parents tended to have taller children. You can do numerical summaries. You can talk about a correlation matrix or a covariance matrix. That's maybe useful to you as the statistician. It's probably less useful to the domain area scientists that you're talking to. If you're talking to somebody who is very knowledgeable about agriculture and fertilizers and things, but they throwing a big box of numbers at them is, I have not found that tends to be very useful. But again, you can do some graphical summaries. I think the main one in my mind would be just make a scatter plot. I think that tells a lot of the story. Now, this next slide talks about n-dimensional exploration. Now, we have a good example with Galton data. Instead of working with mean parent height, which is kind of artificial, we're gonna do that here very shortly. But we really have two explanatory variables, right? Our response variable, the variable that we're thinking is the response, will be the child's height. But for our explanatory variables, we've got father's height, we've got mother's height. So if we want to understand the relationship, if we wanted to simultaneously explore the relationships between n variables, that's absolutely the goal. And it's really hard. Try to make a 3D scatter plot. You can do it, and there's some pretty cool visualizations, but I think it's really hard for us to interpret them. And so you rotate them and stuff. They're cool to look at. You have to ask yourself, is this going to be valuable to the audience that I'm trying to tell my story to? I think just as effective could be just a sequence of scatter plots where maybe you've got child here, you've got father here. We would have some data. We'd have child, mother's height. We'd have some data. We could see how each of those are related. We could even look and see if mother's height and father's height are related. I bet they are. Tall people tend to end up in relationships with tall people. That's not universal, but I think that's there's a reason that height is asked on dating sites, I think. So the and that would be useful. Now this plot is different. We'd have to be careful with we'd have to be very careful when we're explaining it, because the meaning of this plot here, where we have an explanatory variable and a response variable, is very different between a plot between two variables that we're going to treat as explanatory. We're not trying to understand in Galton was not trying to understand anything about dating, about relationships between father's heights and mother's heights. Galton was driven about biology, about genetics, and how the father's genes that make him tall are passed along to the child. And so that's, the idea of what's explanatory and what's response is very much driven by the question that's being asked. In this setting, it's clearly the child's height that would be the response. And so what is the point of this? Well, down the road, of course, we're going to be talking about multiple regression. And if we have two explanatory variables that are highly correlated, that's going to be meaningful to us. That's going to have implications for our model and our parameter estimates. And we as statisticians might want to know that. And so a plot like this could be useful to us, might not be anything that we pass along to the end user. It might be something that we just use so that we understand our problem a little bit better. Okay, so here is, let's see, what do I want to say about Galton here? Yeah, let me step through this just a tiny bit. Okay, and then we'll get to simple linear regression. So just wanted to make sure I was thinking about this the way I wanted to think about it. So Sir Francis Galton was, when he was writing this paper, he wasn't Sir yet. He hadn't been knighted yet, but I'm pretty sure he is Sir. He became Sir Francis Galton. He was interested in this question about how, basically, how understanding genetics, so how a child's height could be influenced by a parent's height. Now, I did not meet Sir Francis. He doesn't seem to be a very positive guy, because you notice that title of the of his article here, his manuscript, is Regression Toward Mediocrity. So that's kind of a negative connotation. What he found was that, yes, there was a positive relationship here, and but that the slope of the line is less than 1. For every inch that the parent's height increased, that did not mean that the average child's height would increase by an inch. And so that's what he meant by regression toward mediocrity. Yeah, your child may be, if you are taller, your child may tend to be taller, but the influence is not 1-to-1, I guess is the way that the way I would describe it. So so anyway, this term regression, which is, basically the primary focus of this class, came from Sir Francis Galton. It came from this article, and it really came from this idea of the influence of height is less than a 45-degree line. And unfortunately, that term regression has stuck around. It's we use this term so often in statistics that we don't really think of the negative connotation that regression probably has in the minds of the people we're talking about. Oh, we're going to perform a regression analysis, unless they've been in a statistics class. Regress seems like the opposite of progress, but that's, of course, not how we intended. What we're going to do is we're just going to eventually build a regression model which relates our explanatory variables to our response variables. Okay, so that's a little history, useful because Sir Francis will come up often when people talk about regression anyway. We'll get to regression later in the next video. For now, we're just gonna do our exploratory data analysis, and we've seen the outcomes, but what I want to do is look at the code a little bit. In class, when I'm in class with you, I'll probably be running a lot of this R code that appears in the slides kind of live. It's a little difficult to jump back and forth, and this is pretty direct, and so I'm just going to talk through it, but it's important that we understand it. So hey, we're going to use ggplot because it makes nice plots. ggplot is something that I personally don't use a whole lot, and that's maybe because I'm a dinosaur. But it's really, really handy and really makes nice plots. So here we're just loading that data. Of course, we have to give it the right path so that our computer knows where to find the data, but there is a data file called Galton, which you can access. It will be posted on Canvas. As I'm making these videos right now, I haven't posted it on Canvas, but need to. Let's see. Okay, so ls is kind of like list. If you're familiar with Unix code, that's right from Unix. It's just going to tell us everything that's in R's memory. And so we've got these 4 are objects in memory from reading in this data set. The main one that we want to look at is the R object called Galton. And if you use the command head, again, this agrees with Unix type stuff, it's going to give you the first few lines of the code. And so we have a family code. We can see here that this is a family where they have 4 children, and so of course the father's height is the same for all 4 children, as is the mother's height. But here are the kids' heights. Now, what we're going to do is, because we're going to start off with simple linear regression analysis, probably, we're going to take these 2 explanatory variables and convert them down to 1 explanatory variable. Let's just take their mean height and let's see how our response variable, which is kids' height, is affected by mean height. And if you're thinking, well, that's not the best way to handle this data, I would probably agree. I think it would be better to do a multiple regression analysis of down the road, but for now, let's just do that because it's simplifying and maybe we can learn something through this. So our explanatory variable, which we're usually in this class going to denote by X, is the mean parent height. Y is the adult child height, so that's that guy there. And we always start by inspecting the data. So this is the exploratory data analysis. Before we fit a model to this data, hey, let's make some pictures. So in this next one, we're going to create this thing called GM, which comes from Galton. We're selecting parent height. We're going to create this new variable called parent height, and that's going to be equal to the explanatory variable X from the previous slide, from parent height. Child height is going to be our new variable, which is equal to height. And recall that on this previous one, we didn't actually call the data set that we read in, we didn't denote that as child height, and it'd be a little bit cleaner to make it very clear to the user that, hey, this is our response variable child height. All right, so then what we're gonna do is make a kind of a joint histogram here of child height and parent height. And so here is our histogram of children's height. Here's our histogram of parents' height. One thing that we notice right away is it appears that the spread of the data, notice that these, we're roughly on, I guess we're on the same scale here. We're going from 55 to 80 in both of these. We see more spread to the child's height. There's a mean of about 67. Yeah, the mean is not too different between these two, but clearly the child height is more spread out. Why do we think that would be? Well, if we pause and think about it for a second, why should child's height be more spread out than parent height? Hey, remember, this is mean parent height, right? If we take means of variables, we tend to, the variance tends to decrease. And so, so I think that's what's driving this noticeable difference in the spread between the two histograms. Here is basically a picture that tells the same story in a different way. We have the box plots. We see that the interquartile range of the child height is greater than the interquartile range of the parent height, and the outliers, or the whiskers of these box and whisker plots, are much smaller for the parent height than for the child height. And here is our code to make a nice plot of this data. And then finally, here is that that scatter plot, which I was referring to before. This really is the one that's going to talk about the relationship between the two variables. So everything that we did before, I would categorize as a 1D analysis, maybe done in parallel, but we didn't talk about the relationship between these variables. Here we see that relationship. And here's our code for making this scatter plot. Okay, I guess. So, one can imagine that if this data weren't 150 or close to 150 years old, if we were just collecting this data, we would be asking questions like, is there a relationship between parent height and child height? How do we describe this relationship? Does it appear to be linear? Our first models are going to be simple. They're going to be simple linear models. And so we're going to draw a line of best fit through that data. A question one needs to ask is a line a suitable model, or do we need a more complex model for describing the relationship adequately? How can we measure the strength of the relationship? I said before that there's kind of a weak relationship here. What do I mean by weak relationship here. It's sort of described by this cloud of points where we see an upward slope, but it's not dramatic. And that slope seems to be at least partially overwhelmed by the spread of the data. So of course, we can describe the strength of the relationship through things like correlation. And so that's the direction we need to go. That's not a tool that Galton had back in 1886. To what extent is the variability in child height explained by its association with parent height? This is something in regression analysis that we love to do. We're explaining so much percent of the total variability found in the response variable. We can, how can we use this relationship to estimate mean child height given parent height? So if the mean parent height is 68 inches, what do we expect for the child height? Another way in this simple model is talking about it is prediction. The estimate of the mean and prediction, those point estimates are one and the same. But we also want to talk about the uncertainty associated with the expected value, the mean value given a parent's height is 68. And we want to talk about the uncertainty of a prediction. If I know that the mean parent height is 68, what would be a 95% prediction interval as opposed to a 95% confidence interval for the mean? So the uncertainty with those questions is different, and that's something we will describe in this class. So this is kind of, these first two bullets are really about estimation versus prediction. If those terms are not different in your mind, that's okay. But at this point, all you need to know is they will be. And talking about the accuracy of both of these things is something that we're going to find out is different. The uncertainty associated with the estimate is going to be different than the uncertainty associated with the prediction. Okay, so those are the slides for exploratory data analysis. And again, this is an important part of a data analysis. It's something as an instructor, one doesn't spend a whole lot of time on, but as a practicing statistician, you are going to spend time exploring your data. We're going to think carefully about it. And really, I think the takeaway message for EDA, and so let me try and write this as best I can here. So the takeaway message is, I think of EDA really for two purposes. You can do exploratory data analysis, really thinking about the exploratory part, and that's trying to get an initial understanding of the data. What are the relationships? What, and some of those things that we talked about earlier, are there outliers? Are there miscoding? And then using it further to guide us in what kind of model are we going to use to analyze this data. But the second piece, and this kind of is what I think was done with the pictures that were shown in the slides, is trying to tell the story. Your job as practicing statistician is to tell the story. If you go in and you say, well, the estimate of beta 1 is 0.7, so what? That's not telling the story. You're going to use exploratory data analysis tools. You're going to use graphs and pictures and to tell the story. So EDA methods can be used in non-exploratory mode to tell the data story. And as a practicing statistician, if you can do that, you're going to be super valuable. Anybody can download R and run a regression analysis. But if you can't tell a story, then how valuable was that analysis? Okay, I am going to stop here and Let me do that. So thank you for watching these videos. I again apologize that I'm not there this first week of classes. It's very inconvenient that I'm not. So I appreciate you watching these videos, and I will be posting some more videos to take care of the lectures for the rest of the first week. So thanks, and I'll see you soon.